Hello, my name is Zach, and today I'm here to talk about the update coming in OpticStudio 17 for the phosphorescent fluorescence model. Um, the kind of two major changes are one, we are trying to more accurately model the actual number of rays which are absorbed and re-emitted, and two, we've made the absorption spectrum have a wavelength dependence. So I'll show you kind of how this works with this simple system here. I have a rectangular volume which has a phosphorescent fluorescence model. Then I have a source ray, and you can see over here there's a small absorbing detector rectangle which is going to catch unabsorbed light, and then all of the re-emitted light will be caught by this detector polar here. If I open the object properties on this detector, or excuse me, on this volume, go to volume physics, you can see here the phosphorescent fluorescence model, and you can see that the first four or so inputs on this are unchanged. We still have the absorption, emission spectra, and the excitation or quantum yield. And here today I'm just using a simple absorption spectrum, which absorbs between 200 and 400 nanometers, and it absorbs longer wavelengths a little bit more efficiently. My emission spectrum is just a flat emission between 400 and 700, and then my quantum yield is just going to be 1. The new parameters down here are the extinction coefficient, the extinction wavelength, and the phosphor density. So the phosphor density is entered in units of, or particles per centimeter cubed, and then the extinction coefficient is defined at this extinction wavelength, and then it's scaled according to these two inputs and also your absorption spectrum for all incident light. So we have some extinction factor that's applied to each, for any incident wavelength, and that's how we end up scaling the mean free path according to wavelength. So, oh, and one more thing, we also have this me-scatter model that kind of goes along with the photoluminescence, but we have the mean free path set here very long, so we won't see any effects from this today. So with these settings, I'm going to go ahead and run a ray trace. Notice that I have the wavelength set to 250 nanometers, and so because of the less efficient absorption spectrum for this wavelength, we should see our light will have a longer mean free path in this object, which means less of it will get absorbed and re-emitted. So we can see here for 100,000 incident rays, we got 27,000 re-emitted onto our detector polar. Now let's try increasing this wavelength. And we'll see now, if we rerun the ray trace, these rays will be more effectively absorbed and re-emitted, and so we should have a greater number of rays being re-emitted onto this detector polar. And we do see that happening. One thing to note about this model right now is that there's actually a bug that was discovered in-house where we aren't properly preventing re-emission into shorter wavelengths. So it's kind of a problem, and we're working on fixing it now, but just keep that in mind during your testing. Maybe keep your absorption and emission spectra so they don't overlap in order to prevent re-emission into a higher energy ray. But that is all for now, so thank you very much.